Welcome to my short presentation on DC calculations. My name is Konrad Janson and I'm going to try to explain a complicated theory. Try to make it as simple as it possibly can for the novice learner. Let's have a look at some of the things we're going to present this morning. First of all, there you can see a simple series circuit. One single ring, 4 components, 100 volts. 2 capacitors and 2 resistors. We're going to calculate first of all the total resistance and total capacitance, and I'm going to fill in these little sections in the center of the circle there with the questions that are unanswered. For example, the total current, the total wattage, the total charge, and what they call the time constant or tau value. And then from that we're going to work out the total charge of the entire circuit, how long it takes to charge and also to discharge this circuit. To assist us in this task, we've got some little tools here that we can use in regards to these particular triangles, which show us basically how to calculate voltage in this example here by multiplying the resistance and current. Or if we've got the voltage already and we know what the total resistance is, we can then divide the voltage by resistance to equal current. Of course, once we've got voltage and current in this orange triangle here, we can calculate the total power by multiplying voltage and current. We get the total wattage. So you can see over here also in this green triangle, if we've already got the voltage, which we do at 100 volts, and we can calculate the total capacitance, and I'll show you how to do that very shortly by adding these two values of capacitance and then inverting the fraction to get the total coulombs, the total capacitance, and then multiplying it by the volts to get the total coulombs. Finally, once we've got the total resistance and the total capacitance, we multiply that value, we end up with a time constant value, which when multiplied by 5 time constants, we end up with the total charge. There are some basic rules that we follow when we calculate things in series and parallel circuits. And you can see up here that we've outlined the rules as far as series are concerned. First thing I want you to take a note of is this voltage calculation. The voltage over 1 and the voltage over 2 should equate to voltage total if there are only 2 components in this circuit. So that's how we're going to calculate the voltage, by adding the voltage drop, and we should end up with a total value of 100 volts. Now, in this example, being a series circuit, we're going to find that the current is exactly the same no matter where we measure it. The current will always be the same, and that will be the total current value, which we calculate over here by dividing the voltage by the resistor. That also equates the same for power or wattage calculation. So the wattage calculation should be the same no matter where we measure it in the circuit. Now, when we get into parallel rules, there's a different set of rules in regards to that, because here in parallel, if we have two resistors in parallel, then the voltage would be equal in both of those resistors and also capacitors. But the total capacitance is added. So in a parallel world, we add the capacitor value. So if this was in parallel, it would be 100 plus 200 equals 300 microfarads, but it's not, it's in series. There's another special rule we use to calculate capacitance and resistance when it's not equating to these rules. So here, we definitely add the resistors to get the total resistance, but calculating capacitance in series is different. Here I've outlined the rules in regards to that, inverting the calculations. For example, if we get the calculation over here of 100 microfarads and 200 microfarads, we can use the calculator to invert the fractions there to get the appropriate amount of capacitance in total for the circuit. Let's bring the calculator up. When we bring the calculator up here, we can just put the two values of 100 microfarads and 200 microfarads in a particular fashion to get the total capacitance. Let's do that one first. So 100 And in the micro range, we need to push the exponential micro minus 6 to come up with a number. Once we come up with that number, we hit the 1x button, which is that inverting fraction, and we end up with 10,000. Now we add that to the second capacitor of 200 microfarads. So again, 200, again, exponential minus 6 is in the micro range, and then 1x. Once we end up with this number of 15,000, we hit the 1x key yet again to end up with a total of 6.66 to the minus 5. Now what does all that mean, 6.66 to the minus 5? Well, what that means is 6.66 to the minus 5, that's where we have the total amount of capacitors. Let's see how that works out. So how do we express that 6.66 to the minus 5? So let's have a look at that number, that 6.66 to the minus 5. So how we write it out is 0.00000, and it's minus 5. So the first number should be at that minus 5. So if we have a look at that number there, we'll see that the first 3 digits there are in the milli range. It's not in the milli range, it's actually over here in the micro range. So what we see there is 0.66 in the micro range. That's expressed as 66 microfarads. Let's put that value in of 66 microfarads. So 66 microfarads is expressed in that U, what's that U number or letter. It tells us that it's in the micro range. So once we've got that, we've got quite a lot of information now on the screen. We've got the total voltage, which is 100 volts, and now we've got the total capacitance, which is 66 microfarads. And to get the total resistance, as you can see up here, it's pretty straightforward. It's basically, R1 plus R2 equals R total. So it's just 50 megohms plus 100 megohms to give us the total of 150 megohms. So we can actually type that into this area over here. Complete it there. I just want 150 megs, that should be sufficient, right? So now if we have a look at the clues that we've got left on the screen here, we've calculated, we know what the total voltage is, we know what the total resistance is, we know what the total, well, we don't know what the total current is, but let's calculate that up next, all right? So again, we've got this 150 megs divided by 100 volts. So let's bring the calculator up again. And of course, it's 100 volts divided by 150 megs, which is 150 exponential 6. And we can equate that as, again, 6.66 to the minus 7. How do we write that? Well, again, if we're looking into that minus 7 range, it's 0.000000, and in the 7, minus 7. So let's have a look at that number again. So this is the milli. This is the milli range over here, micro range, and then underneath the micro range, 1, 2, 3, 4, 5, 6, 7 is in the nano range. So now we've got nano amps. That's the answer in this particular example, the total amount of amps. So let's write that in. Not a lot of current, but nonetheless, that's what the answer is. Okay, so now let's have a look at what we've got completed here. We've got completed so far the total amount of voltage, total amount of resistance, total amount of current, so we can circle that one off, we can circle that one off. As we move across our little process over here, we can now complete the total amount of wattage as well. So let's bring the calculator back up over here. We'll see what total wattage equates to. According to our calculations here, we've got the total amount of current and the total voltage. So it is 100 volts multiplied by 666 exponential. Now it's in the nano range, so it's -9. And that equals that. So what have we got? 1, 2, 3, 4, 5, 6. So in this range over here, it's in the micro range. So it's 66 microwatts. We can write that in now as well. So now we can circle off the amount of wattage. So far we've calculated quite a lot, and we've still got this voltage and we've still got this total capacitance cleared up, and again we've got the total resistance and the total capacitance. So if we've got 2 out of 3 of these clues, we should be able to work out the third point in this, which is the total charge measured in coulombs. So we bring our calculator back up, we can do that. So according to our little triangle, the total coulombs, or total charge in a capacitance series circuit, is the total capacitance multiplied by voltage. So we can see over here 66 microfarads multiplied by 100 volts. So 100 multiplied by 66 in the micro range, so exponential, -6. And we should equate to this number, which is 6.6 millicoulombs. That's the answer. Let's type that in. 6.6 millicoulombs. So now what we have is we've completed this particular part of the arrangement where we've got the total amount of charge. That comes in very, very handy when we want to calculate the total voltage drop and total current moving forward. But let's complete this particular calculation that we've got over here by calculating this one here, which is the tau, or time constant for this circuit, which is resistance multiplied by the total amount of capacitance. So let's do that calculation now. Let's bring the calculator over again. So the total amount of resistance, as you can see over here, is 150 megohms. So how do we write that? Is we write that by putting in 150 as exponential 6 being megohms. And we multiply that by the total amount of capacitance, which is 66 microfarads. So multiplied by 66 exponential micro minus 6, and we should end up with that 9.9 or 9,900, and that's measured in seconds. So let's put that in. Now to calculate the total charge, we simply multiply that by 5 and we'll end up with the total charge. So multiplying that by 5 would equate to about 49,500 seconds. That's very, very slow charging time, obviously, for this particular circuit, but that's the sort of number we're looking at there. We can convert that to minutes and then into hours and then into days and weeks and months if you're required to do that, but that's the basics of that. So let's move forward here and have a look at calculating, for example, the voltage drop over this particular capacitor. How do we do that? So again, we've got the clues over here. If we want to work out voltage, then we look in this area over here where we've got the total amount of coulombs, and we've got the total amount of the total amount of coulombs and the total amount of farads, And by dividing coulombs by farads in any particular part of this capacitance circuit, we can calculate the voltage drop. So let's bring the calculator back over again and have a look at how we do that. So we can see there it's 100 microfarads, and the total amount of coulombs is over here 6.6 millicoulombs. So 6.6 millicoulombs divided by 66 microfarads. So let's put that in. 6.6 exponential, it's in the milli range, so it's -3, divided by 66, and this is in the micro range, so exponential -6, and that should equal 100 volts. That equates to the total voltage. Now let's have a look at the voltage drop over this particular capacitor here, which is 100 microfarads. So again, we get this 6.6 exponential -3. Now we've got millicoulombs, and we're going to divide that by 100 exponential -6 microfarads. So what that should equal should be 66 volts. So again, the voltage drop over that particular capacitor is at 66 volts, and we can write that in now as well. So again, you can see how we calculate the capacitance and the voltage and the total coulombs or charge in a particular capacitance circuit to get these voltage totals and voltage drops as we go through the circuit. We can do the same thing again for C2. To do that, we'll bring our calculator over again. We'll do the same thing. So it's 6.6 millicoulombs, so exponential -3. And we divide that by, what's the value over here? 200 microfarads. So 200, it's in the micro range, so exponential -6. And we equal 33 volts. So we can type that in now, 33 volts. So again, you can see how we calculate these circuits, and of course V1 plus V2 equals V total. That looks about right to me. Okay. Now in current, of course, being current in series, we can see there that the current should be equal. Should be equal everywhere. So whatever the total current is, basically that's what the total current should be, also at R1 and R2. And we can see that the total current is 666 nanoamps. So that's the answer to that one. So we can simply type that in because we know that these equations up here are equal. So again, 666 nanoamps is the answer there. Pretty straightforward, I think. And of course it would be the same there as well, 6 nanoamp, because it's equal. To give you the concept there of what's going on, there's the rules, and this is how we apply them. So that's about it, really. Thank you very much for your attendance and your concentration. I hope that helps, and let's practice. Practice, of course, indeed gives you the skill set to make this a lot easier. Let's practice that in the future, and good luck till next time. It's Konrad Janson signing off.